In the last lecture, we already talked about one of the parameters for measuring the damping of a weakly damped oscillator, which was the decay constant, or we call it the relaxation time. So what was the relaxation time? The relaxation time is the time required by a weakly damped oscillator in which its amplitude reduces to 1 by e times of the initial value. So if you take a weakly damped oscillator, that means we are talking of the B less than omega case, or we also call it an underdamped oscillator. Now the time in which the amplitude of oscillation will reduce to 1 by e times of the initial amplitude, that is what we call the decay constant or the relaxation time. And in the last lecture we have shown that this tau relaxation time comes out to be the inverse of the damping factor B. So 1 by B is the relaxation time. So what it means is that if you increase the value of B, that means if the damping is slightly increased, then the relaxation time will reduce. Or in other words, we say that higher the amount of damping present, less will be the time for which the oscillation is going to continue, and vice versa. Today we shall discuss about a second parameter which is also used for measuring this damping, and this second parameter is called the logarithmic decrement. So if we recall that the displacement of a weakly damped oscillator, that means in this B less than omega case, the displacement expression is given by c e to the power minus bt sine beta t plus some theta, where this beta stands for root over of omega square minus b square. So beta in this case, for this weakly damped oscillator, this beta is the angular frequency, and hence we know that the time period is written by 2 pi by beta, so that will be 2 pi root over of omega square minus b square. So for a weakly damped oscillator, this 2 pi by root over of omega square minus b square will be called the time period. Let us denote it as some t prime, just to distinguish it from the time period of a free oscillator, which we represented as capital T. So here we use the notation t prime for the time period of a weakly damped oscillator, and it is given by 2 pi root over omega square minus b square. Now, so if I draw a graph of this displacement versus time, we have seen in the last lecture that this graph will appear like this. So what we find is that the amplitude of oscillation gradually decays with time, and this envelope will be like the e to the power minus bt curve. So this decay of amplitude is exponentially decreasing in time. Now let us say that at time t1 the amplitude value was a1. Again, at some time t2 it has reached another amplitude, but now it's a reduced amplitude and its value is a2, and so on. So if you look at this expression, you will understand that at this amplitude positions on either side of the equilibrium, if we see at this amplitude positions, this sine beta t plus theta, this part will either be plus 1 or minus 1. So if I take this upper side as positive, so at these points sine beta t plus theta has the value plus 1, whereas at these points on the other side of the equilibrium, on the negative side, sine beta t plus theta will have a value minus 1. So the value of the displacement at these amplitude points is given only by this term c e to the power minus bt. So you see a1, this amplitude value this occurs at time t1. So a1 is c e to the power minus b t1. Similarly, a2, which is my next amplitude on the same side of the equilibrium, that would be c e to the power minus b t2, and so on. So an would be some c e to the power minus b into tn. If we take the ratio of these successive amplitudes on the same side of equilibrium, so what we do is, let us calculate this a1 by a2. So this a1 by a2 is c e to the power minus b t1 divided by c e to the power minus b t2. So this c will cancel, and if you calculate, you get e to the power b into t2 minus t1. So if you keep this minus b, then it will be t1 minus t2. So I have taken this negative sign inside, so it becomes b into t2 minus t1. Similarly, if I do a2 by a3, so a2 by a3 will also be like c to the power minus b t2 divided by c to the power minus b t3, where a3 is this particular amplitude occurring at time t3. So here also, if you divide, it gives you e to the power b t3 minus t2, and so on. Now look, what is this time t2 minus t1? t1 was the time at which we reached this first amplitude position. t2 is the time at which we reach the second amplitude point on the same side of the equilibrium. So the particle goes from this point to the other side of the equilibrium and comes back to the amplitude point again in this time difference t2 minus t1. So this t2 minus t1 is nothing but the time period of the oscillator, because remember that what we call the time period is the time required for one complete oscillation. So if the particle starts from this amplitude, goes to the other side and comes back to the amplitude on the same side of the equilibrium, that is one complete oscillation of the system, and that time required is what you call the time period. So t2 minus t1 is the time period of oscillation. So this ratio of a1 by a2 becomes e to the power b t prime. Similarly, t3 minus t2, so from a2 it goes to the other side and comes back. So t3 minus t2 is another time period. So this is also e to the power b t prime. So as you can see that this ratio a1 by a2 or a2 by a3 remains fixed. So in general we can write some a n minus 1 by a n. This ratio would be e to the power b into t prime, where t prime is the time period of the weakly damped oscillator. This ratio of successive amplitudes, which remains a constant for any two successive amplitudes you take, so an minus 1 by an, this ratio of successive amplitudes on the same side of the equilibrium is what you call the decrement. So D stands for decrement. So if I take the log of D, so log of D will be equal to log of e to the power b t prime, and that is equal to b t prime. So this logarithm of the decrement means the ratio of successive amplitudes on the same side of the equilibrium. Logarithm of the decrement is what you call the log decrement lambda. So this lambda is called the logarithmic decrement, and our analysis shows that for any weakly damped oscillator, this logarithmic decrement is equal to the damping factor b multiplied by the time period.